Same way. So if I ask to compare these two graphs, so we know their absolute value, okay? What is the shape of an absolute value graph? Ben, a V shape, okay? So now if I asked you to graph an absolute value, I want to see both sides of the V, and I want to see the point of where that V is at. All right, so just absolute value of X, we could make a 2-column chart. And we could say, all right, if we're at -3, it's going to be a +3, -1, +1. It will look just like that. All right, and if we were to graph it, it would look that V shape with the point of the V right at the origin. All right, if we change things up a little bit, and we said now 2 times X in absolute value bars. Any predictions on what that's going to do? What's that 2 going to do to this red shape that we got going on here? I'll give you a hint. Is it going to be narrower or is it going to be wider? Okay, I heard a mix there. What's going on? Okay, so let's try. So we know if we do 0, 2 times 0 in absolute value bars is still going to give us 0. If we did, say, a -2, and so 2 times -2 would be -4, but still in absolute value bars, so that brings us to a +4. If we did -5, we'd have 2 times -5, which is -10, but it's an absolute value bar, so it'd be a +10. Reflecting these over, because we know it's this V shape, we'll have all these points. So -2, 1, 2, 3, 1, 2, 3, 4, and then 5. 1, 2. Be up here. And so we can see this one starts to go like that. It's going to do the same thing on this side. It's going to look like that. So that 2 on that actually made it a little narrower. Or you can think of that 2 is making it shoot up faster. Okay, so that's how I think of it, because when we were at 2 on our red graph, we only went up to right here. When I put 2 in here, I'm up right here, but now I'm multiplying by 2, so this point's obviously double. So it's shooting up faster, so it actually makes our graph narrower. So it's a little counterintuitive on what's going on there. How I think about it as the output is 2 times as fast, it's going up faster and faster. Okay, so let's expand on this. So if I had the graph y = x squared, so we've done that one. We know that's a parabola that opens up. We made some points. We know 0, 0 is going to be the vertex of it. -1 squared would be 1. -2 squared would be a +4. This would reflect over to 1, 1, and a +2 and a +4. So we'd have here 1, 2, 3, 4, here. So we have our parabola. It looks like this. So this is our basic function. Our parent function is just this parabola. Now if we were to change this up, and I'll do 3x squared. So if we're thinking width, is this 3 going to make it narrower or wider than this red graph that I've already drawn? Is this 3x squared going to go inside of this red line, or is it going to go on the outside of the red line? Inside. Okay, so this is just like that absolute value. This multiple of 3 actually makes it narrower because it's shooting up faster. So still we'd have 0, 0, but now at -1, we're going to be at 3. At -2, we're going to be at 12. And we continue on, 1, 3 to 12. So -1 now is going to be up at 3. -2 is going to be way up here at 12. And so this creates a parabola that is narrower. And we know standard form of a quadratic is in this y equals ax squared, where a represents some number. So in this case, in our middle column here, a is 3. And so if our a value is greater than 1, it makes it narrower. It makes our graph narrower in relation to just that basic function. Well, let's do this next one too, so now if I have 1/2 x squared, so my a is less than 1, I'm still going to have my origin here at 0, 0, but now my output is going to be half as large. All right, so if I went to, say, a -2, I would end up with 2 for a y value. Now if I went +2, I would end up with +2 again. So -2, 2 is going to be right there, and then +2, 2 is going to be right there. It would actually expand out. So if my a value is less than 1, my graph ends up being wider than the parent function. So these ones are a little counterintuitive. Multiplying by 3 actually makes it narrower, or how I like to think of it, it's shooting up faster. That multiple of 3 is actually making it go up faster. And that multiple of 1/2, it's not going up as fast. It's going up at half the speed. And so that's why it's making it, in a sense, wider, or appear to be wider. I have on here this interval of a greater than 1, and I have an interval of a less than 1. But more specifically, I'm going to clarify that and say when a is between 0 and 1 is when it's wider. Why am I putting a lower bound at 0? What happens if I put a negative in there? Okay, if it's negative, so if your a value is less than 0, it reflects over the x-axis. And so I don't have one on here, but let's do one real quick. So if I were to do, if there was y equals -x squared, we know all that means is it's going down. So if there's a negative in front of it, it's just going down. If it's a positive, it's going to be going up. But now that actual coefficient of a tells us what's going on. Is it going to be narrower or is it going to be wider? So we could have narrow or wider graphs still going down. Okay, let's graph some square root functions. So this was a basic function that we talked about the other day. Square root of x. What happens if I put 0 in there? What is the square root of 0? 0. Okay, and that is a number. So that's telling me I'm starting right there at the origin. What about square root of -1? Can't do it. That is undefined. Okay, so it's never going to dip below the x-axis or go to the left of the y-axis. So now I can start going positive values. So +1 is 1. I'm going to go up to +4, which is 2. And so I have 1, 1, and then I have 4, 2, and then we keep going from there. So that's my square root of x, that basic function that we talked about if we change this up to say negative of square root of x? What's this negative do again? What did we just talk about? It's going to reflect it over the x-axis. And so now we're going to have down here this exact same shape, but it's all going to be down below the x-axis. And we can check that doing some points. So we know 0, 0 is going to be 1. If I chose 1, that's saying negative times the square root of 1, which is a negative 1. So I have this point here of 1, negative 1. So this is an order of operations 1. This negative being on the outside, we're going to do the square root piece and then multiply it by negative 1. Or whatever number we get, we just have a negative of that. Okay, same thing, if I were to put 4, square root of 4 would be 2 times a negative 1 would be negative 2. So I'm going to be down here. So that negative, all it did was reflect it across the x-axis. And now this last one, if we have a negative inside of here. So we know we can't graph imaginary numbers. So we've seen this before. If there's a negative under a square root, we can use that imaginary unit I, and we can work with it. Well, in this one, we're not going to, you can't graph imaginary numbers. So that's going to change what domain values I can put in here. So I can still start at 0. So if I put 0 in there, negative 0 is still 0. So that's going to put me at the origin. That's a point. But now, if I chose, say, 9, that's saying I'm going to take the square root of negative 9, which isn't possible. So my domain now is restricted. I actually have to input negative numbers. So positive numbers are not in the domain of this function, positive x values. So if I put in negative 9, that tells me I have the square root of a negative times negative 9. So that's really square root of positive 9, which is 3. So negative 9, 3 would be a point. If I did negative 4, I would have a negative of negative 4. Square root of that would be 2. If I chose negative 1, I would get an output of positive 1. So this one actually goes that direction. So we can see from the middle column that this was a reflection over the x-axis when that negative is attached. So if my input is being changed, that actually reflects over the y. Okay, so these are all, this green and this purple are reflections from this initial red line, but it just depends, okay? Is it a negative of the function? So this one you could also write, we could also write this as negative of, change my color to keep it consistent. A negative of f of x. And then this third column was f of a negative x. So those are distinctly different. That middle column, I'm taking a negative of whatever my output is. But in green, I'm going to do, before I even do any work, I'm going to take a negative of whatever my input is and then keep going. So that's how we were undoing, essentially, this negative piece when I put a negative in there. And all of these, if you're not sure how to graph them, or you're not sure where the points are at, 2-column chart's the way to go. Make a 2-column chart, start putting points in, and then that will create your graph. You'll know exactly what it's going to look like. Let's talk about symmetry. So symmetry is very, very straightforward, but we're going to dive into it a little bit more. So we can see that this graph is symmetric. And is it symmetric about the y-axis, or is it symmetric about the x-axis? Matthew, what do you think? Not both, because it would have to be correct. Okay, so this right here is the axis of symmetry, because this point does not reflect up to a point over here. But if I were to pick a point to the right, this does reflect right over to that. So this is a reflection about the y-axis. So I have up here, the graph of an equation is symmetric with respect to the y-axis if the replacement of x with negative x results in an equivalent equation. What that means is we have some point here, we'll just call it x comma y. Well, this point over here is a negative x comma y. My y stayed the same, but the x is the opposite sign. Okay, so what this is getting at is if your x changes sign, your function is symmetrical about the y-axis. And we're going to do some practice with this too to actually show you why this works. Right, some examples too, we could say, we know like y equals x squared is a reflection about, or is symmetrical about the y-axis. We know like y equals square root of x is symmetrical about the y-axis. And whatever x value I have on one side of the y-axis, I can have the opposite x value on the other side, but my y-coordinate does not change. The x-coordinate is the only thing that would change. We can have symmetry about the x-axis as well. So if I chose 2 points on here, I can see those are symmetric. This is some x comma y, but this is x comma negative y. So this one, if it's symmetric about the x, there'll be a replacement of y to negative y, or vice versa. Okay, I'll put these up too if you didn't get everything. All right, so these are the types of problems now you'll see. Is they'll ask you to test for symmetry, and they'll give you an equation. They'll say, okay, is it symmetric about the x, or is it symmetric about the y? So the first one, y equals x squared plus 4. Okay, so again, understanding basic functions, I can recognize, okay, that's an x squared function. I know that's going to be a parabola that opens up. And so I'm already starting to think, okay, I think that's symmetric about the y. Well, let's just test it real quick. So if we want to check, does this really reflect over the y? That tells me that I started with x squared plus 4. If I were to replace my positive x with a negative x squared, does this still hold true? Okay. If this still holds true, then it can definitely be reflected over the y-axis. Well, I know a negative x squared will be x squared. Okay, any negative number that I square, it's going to become positive. So because these are the same, these two equations are the same, I could say, yes, this one does reflect over the y. And we are testing, it's saying, okay, if we're going to reflect over the y, doesn't matter if I put an x or if I put a negative x, I get the same output. And so when we test, we're literally putting that in. If I thought it was going to reflect over the x, and I put in a y and then a negative y, those are two different equations. Okay, it would say x squared plus 4 equals y, and the other one would be x squared plus 4 equals negative y. Well, that's not true. They both can't be equal to a positive and a negative. Okay, let's take a look at this next one. X equals y squared minus 3. So this one's starting out as an x equals. Well, I know if I change up my x to a negative x, that's not going to work. So let's see, all right, does this reflect over the x? And if so, I can put a negative y in here instead, and it'll get me the same equation. Well, this one's being squared, so yeah, this one does work, because I end up with x equaling negative y squared is the same as a positive y squared. And so I can see that these are the same, so yes, this one does reflect over the x. Let's look at that third one. X squared plus y squared equals 16. We know the first one, A, was a parabola, opens up. Any idea the shape of B? What that one would look like? Yeah, like a C shape. Okay, because this is a parabola opens up. Really, all we do is switch the x and the y, and so that creates a parabola that opens up to the right in that C shape. What about this third one? Any idea what that third one would be? Well, x squared plus y squared equals 16. What about if I wrote this as x minus 0 squared plus y minus 0 squared equals 4 squared? Does that look familiar? Nate, what do you say? What is that? Circle. Okay. So again, having an idea of these basic functions, I know in my head, okay, a circle, yeah, that would be symmetric about the y and symmetric about the x. But let's test it real quick to make sure. So if it's over the y, that means I can replace x with negative x. So negative x squared plus y squared, does that equal 16? Yeah, because that still gets me with x squared plus y squared equals 16. So that checks out. So I know it does reflect over the y. And if I wanted to test it, if it would reflect over the x, then I'm going to replace the y with a negative y. So x squared plus negative y squared, does that equal 16? Yep. That's the same thing. That checks out. So this one reflects over both. Again, understanding your basic functions, knowing what the shapes are before you even do any work, guides you to how to do it correctly. All right, and then one more. So this, we have some coordinate x comma y and some coordinate of negative x comma negative y. Does anybody know what this shape is called? I think I heard it. No. Starts with an H. Nothing? It's Friday. Hyperbola. Okay. Yeah. So this is a hyperbola. Come on. That's all right. I'm not going to test you if you know what this is called. This is more of an extra little bit of math knowledge. Hyperbola. So this one is reflected about what? The origin. Okay. So this reflects over the origin. And so if I have some x coordinates, that is going to change to a negative x, or vice versa. So I'm going to put my arrows going both directions. If I'm at x, it'll work for a negative x. If I'm with a negative x, it will work with a positive x. But also my y can go both directions. If I have a positive y, the negative y will work. If I have a negative y, the positive y will work. So do not get this confused with that last part C that we did on the last problem, where we inputted each one. By just simply changing one of them, that reflects over an axis. By changing both of them, then we can reflect over the origin. Okay. All right, so let's do one quick test on this. So if I wanted to test if this would reflect over the origin, does anybody remember what y equals x cubed, what that graph looks like? Like that S shape. So it's going to look something like this. So yes, we already have an idea. Okay, that should reflect over the origin. If I were to pick a point, see how well if I were to pick a point here, that would be the same as here. So it's reflecting across that origin. So what my rule tells me that I should be able to put a negative x in here, and that will be a negative x cubed, if that holds true. If I take a negative number and cube it, do I get a negative or a positive number as an output? Negative. So this negative x cubed stays as negative x cubed, and I'll drop the parentheses. So my question to you is negative of y equaling negative x cubed the same thing as y equals x cubed? Is that a true statement? Yeah, because you could think of it, if I divide this by -1, this by -1, I end up here with positive y and a positive x cubed. So this confirms that this function would reflect across the origin, because I could change x and y to the opposite sign, and it's still an equivalent equation. Interesting? Sure, I'll take that. For Friday afternoon. Okay. So 2.7 due Monday by class time. Should be able to knock out a lot of it in class here, and you guys have done well on working in class. So continue to work in class. That way you don't have to worry about it over the weekend or Monday morning at 11 o'clock when you realize, shoot, I still haven't done Mr. Army's math homework. He's going to be mad at me.